My name is Tom Holmes. I'm the Chief Actuary for Akur8 for the US region, and welcome to the webinar Actuarial Interpretation of Model Output. We're going to go through a lot of information today. There are going to be various polling questions and various short answer questions that will be answered through the chat. I will say for all of these, just put in your gut instinct. For a lot of these questions, as you might imagine, there's other information that would be useful. A lot of us will have the what if thing that actuaries always do. But throughout this, please just give your gut instinct reactions, and we'll discuss the results. So, why are we talking about this today? Data science is the hot job of, I guess, this millennia, and actuaries are really overlapping in the field. So we are using data science techniques. There are data scientists. I know there have been some discussions with an insurance company of whose scope these models are, who is best suited to build them. And data science has come into the actuarial field so much that there's also a modeling ASOP. There's going to be a new property and casualty predictive analytics exam. And so the question is, are we now just melding and becoming one giant pot of actuarial data scientists? That's kind of up for debate. I would say that there are levels of expertise within actuarial and data scientist purviews that are probably can stick it in one of those two. I would say that there's not going to be one single job just because there's so much to learn in each of these. However, where actuaries will stand is they need to know how to interpret these models and how to solve a business problem. So where actuaries can really shine is by taking the model itself, interpreting it, and knowing what is going to happen in the real world. And I'll say this now, I'll say it again. The statistically best model is very, very rarely the best one for your business problem. And so that is where I think actuaries stand. And that is where we're going to focus on today is really interpreting these models and figuring out what is going to happen when we implement these models, what's happening when we build these models as well. So we're going to start with a couple kind of warm-ups. So open up the chat if you haven't already. And I want people to drop in just what are some purely statistical model evaluation criteria? Just items that, if you are not caring about actuarial considerations, what are these purely statistical criteria that you would look at when building or evaluating a model? P-value. That's the one I expected first. P-value is definitely looked at for GLMs. We have credibility of data. That's huge. That is reflected in things like the p-values, confidence intervals. We have variable importance, AIC, BIC, wonderful. Normalized Gini, consistency across independent samples. I'd say that's a little more judgmental, but yes. How it's validated. Yeah, these are all extremely important things to look at. And a lot of these have correct answers in a way. Like AIC, BIC, does it actually increase? The Gini, does it actually increase as you make these changes? And so now let's switch gears and let's say, what are some purely actuarial model evaluation criteria? Something that when you're looking at a model, you want to make sure that it fits these criteria that are completely separate from what we were discussing before. So again, just drop anything into the chat. The first thing that comes to your mind when you think of actuarial. Intuitive to the public, yes. Consistency over time, dislocation, reasonability. These are absolutely huge. I think the intuitive to the public one is can you file it? Can you use it? Well, if you can't use it, then maybe that's not even worth building. How much did it change from last year? That's a good one, and it combines with the consistency over time, dislocation, practicality, not unfairly discriminatory. Yes, these are all great um, items, and they may conflict with these statistical criteria that we listed before. So when we're evaluating, there's always going to be this balance between actuarial evaluation and statistical evaluation, and that is huge. So now we're going to go to our first polling question. Again, I want you to answer this your gut instinct. What is more important when you're evaluating an actuarial model? Is it the statistical or is it the actuarial components? So I'll give it a minute for the votes to come in. I think we're halfway there, but I have like 15 polls. So if I wait for more than a minute, we're going to run out of time. And so I'll say that this is something that's difficult. I actually had a conversation on this yesterday with some colleagues, just saying which one's more important. I was personally more on the actuarial side, and they were more on the statistical side. And I'll share these results. You should be able to see them on their screen. Here, we're kind of 25, 75 split. A quarter of us think that statistical is more important. 75 of us think that actuarial is more important. And the real answer, as we'll discuss, is it depends. It depends on the strength of these of this support. And so let's talk through some things about building models. So variables and univariates are the first topic of today. And we'll do a very quick warm up, ordinal versus categorical variables to set the stage. Categorical variables have no link. Here we have an example of fuel type, diesel, electric, gasoline, horse, hydrogen powered cars. There's no like real way that I would say, well, in the absence of other data, I'm going to group electric with diesel. Whereas with ordinal continuous variables, maybe you would say, in the absence of other data, I think a 31-year-old should get the same factor as a 30-year-old. Here we're thinking about pricing models specifically. Ordinal or continuous variables could also be A, B, C, D. And the way that you model these variables has a huge effect on how they are fit, obviously. So let's go to our second polling question here, which is accident year. And so I'm going to launch this poll here and say, should you model accident year as an ordinal variable, or should it be categorical? So obviously there is an order to this variable. It's 2018, 2019, 2020. In this case, it even has a little bit of a trend. But there's also some elements here that could be categorical. So I see, I think we're actually already about at the maximum. Yeah, 100% answered. We're going to end this poll. Some people are changing their answers. But here we have a split. It's more like 1/3, 2/3. And so if you're modeling this ordinally, what are you going to get? You're going to reflect things like trend. Maybe you're going to affect things like model things like loss development that do have a pattern year over year. But what you're not going to get in an ordinal treatment is something like one-time shocks, or maybe a very strong change in trend or a level shift in loss development. So personally, I've modeled this categorically most of the time because I think that the categorical treatment will allow it to pick up the combination of trend development and one-time shocks very well. And here I see a comment that 2020 was categorically different, and I would have to say yes. I think especially as you get into something like COVID, these one-time shocks, categorical treatment might be better, even though ordinal continuous treatment makes sense. So again, oh, sorry, I didn't actually share the results of that poll. But definitely, these are the type of considerations that you should think about when you're building the model is which one of these is actually more actuarially appropriate, kind of regardless of what the data field actually is. And so on that note, let's go to this one. This is a tricky question. So let's say if a variable should be ordinal or continuous according to actuarial considerations, but however, a treatment that's categorical fits a lot better, what would you choose? So this categorical treatment treats better statistically. Um, this could be something like a hazard group. It could be something like age. Hopefully not age. Something that has maybe these seven groups to it. It could be anything that you've seen in your data. Um, and so I'll talk a little bit as the votes come in. We have about half of people voting so far. And I'd say this is something where it kind of shows that bias of where do you want to land on that statistical versus actuarial consideration from before. I'm going to end the poll in 10 seconds because I want to share these results. They're actually a little different from before. We're about evenly split here in the group. And this is, I think, very, very telling of the actual decisions of statistics versus actuarial considerations. Um, I again lean very heavily towards actuarial considerations, where this intuitiveness, this fileability is very important to me when building the models. However, as people have pointed out, this categorical treatment may be appropriate. So what are you going to do here? You're probably going to look in and figure out why. Like why is this different? Is there an underwriting reason? Did we collect the data differently? Is our 0 through 7 hazard groups, are they just bad? Like what happened in this group? Um, and so this is another thing that you need to consider. And a lot of these will open up even more questions. And there's a comment in the chat about practicality, sampling, how it's sampled. And so, there's a lot of items to consider. And I think this again, this treatment is something to look into when you're thinking about which one to do. Obviously, there was no correct answer here because there's not enough data, but this will kind of open that discussion. So univariate plots. I'm going to briefly describe what these are. I'm sure everyone is familiar, but everyone plots them in a different way. So here, the blue bars are exposure distribution. We don't have very many older vehicles in this data set. That might be unrealistic. The purple is the observed line. It's maybe 24% higher than average for 1-year-old vehicles. The predicted is 20% higher than average, and the model produced a factor of 1.08. That's a smaller relativity for 1-year vehicles. So when you look at this chart, what are you looking for? Statistically, predicted and observed. You want them to be overlapped as much as possible. You want to look at the volatility of the observed relativities and of the predicted coefficients. You want to say like, are these statistically sound? Maybe here's where you're looking at your p-values, your confidence intervals, making sure that these predictions make sense. Actuarially, as we mentioned before in the introduction, intuitiveness, the magnitude, implementation considerations, all of those things that we had in that very first quiz. And so here, one thing that I don't particularly like is the huge jump between 19 and 20. Fits very well to the data, but probably in practice, we're going to implement something else there. So here are two questions from stakeholders that I think are the most common. And so here we're going to say that our stakeholders have a lot of knowledge about the business, maybe not a whole lot of knowledge about modeling. So here, let's just drop in the chat, why is R predicted so high above the coefficient? How would you explain that to a stakeholder who might not know a lot about modeling? I'll say that everyone who is seeing a model for the first time asks this question. So I'll have a couple. The model is picking up signals from other variables. Cool. Exposure correlation. Yeah, I think it's the combination of those two. It's really the first and 0 year vehicles. They have some other correlated factors that are making it higher. Also, credibility, confounding factors, covariates, all of these are true. I think if I were explaining this to non-technical stakeholders, I would really stick with the correlation and the exposure level, because that I think is the easiest way to explain it to someone who's not a modeler, doesn't have a lot of data scientist background. And so yeah, there's something going on with those 0 and 1 cars that's not related to their age, that's very correlated to their age, that is causing this difference in prediction. And so here's one more question that I see very frequently. A stakeholder wants you to add this variable to your existing model. This variable is not in the model. So given this graph, would you include this variable in the model? Would you say, hey, let's throw it in the model, or would you not include this in the model? So I'll give a couple of moments for the answers to come in. And so again, I'll just talk through the chart here. The purple is the observed values, the gold is the predicted values, and the green is the current coefficient in your model. And so the speedy ones of you are going to be rewarded. We're about at 50% through, but I do want to get through all of our polls, so I'm going to close it in probably 5 seconds here. And see that we're actually pretty split on this. I'm a little surprised here, but there are reasons for this. So yeah, what actual value are we talking about in the model? Exposure losses. So the actual is the observed relativity. Let's pretend this is a pricing model. And so what I can see in this graph is that for the majority of where we have a lot of exposures, where those blue bars are quite large, our predicted and observed are they're following a similar pattern. So what I would get from this is that this variable, while it could be predictive, is already being picked up by a lot of the other variables in our model. So my gut instinct, where I would say is to exclude this variable because it's already being picked up. However, you can always see if there's maybe a little bit additional lift here. But what I would stress to my stakeholder is the vast majority of this signal is probably already in our model. It's being picked up by those correlated variables, similar to the last graph that we were looking at. However, as people in the chat have noted, maybe adding this variable, it's significant. It adds a little bit more tilt. It adds that marginal lift. It's not going to obviously have the full power of the observed you see here, but maybe it'll still improve the model a little bit. So again, we're split because we don't have enough information, but getting that information is part of this interpretation, asking the right questions. Here we have some variable level decisions as you're modeling. So here's a question. I know that this is a little bit of an annoying question here, but let's say removing the log term here significantly increases model performance. So you're removing it, and suddenly your curve looks like this blue one. And then if you leave it in, it looks like this green one, and it'll perform a little less. I would say the main problem with this blue one, as you can see, is that it's really shooting to the moon. And that's one item. And so yes, this is age. It's being captured by driver experience. Why not just test including it and compare without? Can split the data in two. Yeah, I mean, we can do a lot of tests. Obviously, this binary test is not the best, but it's illustrating the point of what do we choose to do with this. And neither of these choices are great. honestly. And can we potentially use both? Um, you can't both remove and include it, but you could maybe take some average in between. I'm going to end the poll here and say that the we wanted to include the log term. And I think if it is truly a binary model or a binary choice, which it isn't, but if it was, I think that's what I would go with as well, just to get this intuitive actuarial shape. However, there's clearly something going on where you have exposure. So where would this improvement come from? If you were looking at this model, what if it significantly increases performance? How would it do that? It would be included, well, where we have exposure. So probably in the middle and left-hand side of this graph is where it is really showing that improvement. So maybe it's coming from that 0 to 12 area. What I will say is that that tail, this is something to be very aware of when you're building an actuarial model with polynomial terms. This one actually has like an x cubed, x squared, linear x term, and then the log term was added to it. What these terms can do is fit where you have the data and extrapolate to where you don't. And so one thing that can happen there is we have to be very careful on the tails that we're not extrapolating to the moon just because it fits very well where we have data. I see there's a hand raised. I'd say go ahead and just type your question into the chat. I will monitor that. We don't have time to get into a huge discussion, but we will have time for Q&A at the end. I just want to get through all of these examples in an hour. In that way, people who are time boxed can get back to work. Again, I will try to remember to share these results sooner. Cool. And so here is one that's possibly more contentious here. Here's one that's we have two credit score model fits. The first model on the left-hand side outperforms the second model on the right-hand side. How do you decide which one to choose? So this way, at least I'm being nice and not saying like a binary choice. But now the question is, what does this mean to you actuarially that we have a worst credit on the left-hand side performing better in one model, and the observed verifies that. Like the observed values are going way, 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 way down for this last bucket. Whereas on the other hand, on the other one we've smoothed it out and we've said, okay, it's going to be consistent. Well, the first response is it's probably noise. Cool. That's definitely one response, and I think that's a pretty good one. What other considerations might you make as you're trying to figure out which one to follow? This is something that maybe from a regulatory perspective, people might say, hey, maybe this is a sign that credit is actually not doing what we want. Maybe people who have very, very poor credit are very careful with their cars. I don't know. They don't want to get into accidents. Um, there's a lot of there's a couple comments around credibility. That's correct. In that far left bucket, there's not a lot of data. So credibility is a huge one to pay attention to here. We think it is just noise. And I think that would also be shown in the test statistics. They would probably not get significantly better going to the right-hand model if we were looking at those results just due to the number of exposures there. Generate friction on model prediction uptake by humans. Yes, people would not like this model on the left-hand side. I see there's a lot of reasonability, buckets too narrow, credibility, counterintuitive issues. And I think those are completely right here. So again, this is what we've been doing so far is weighing those results of statistical versus actuarial considerations. We take those statistical results and you interpret them through the lens of your actuarial knowledge. So here, we've done this so far on the local level. Now let's look at the global level. Let's talk a little bit about these model metrics. We have here a Gini index. That's one that quantifies the model's ability to segment the best and the worst risks. Essentially, Gini is just strictly an order. Can you put these models into an order that makes sense? The second one is the R squared. It's the amount of variability explained by the model. This is dependent on your underlying distribution. So that the higher the R squared, the better the model. If it's negative, it is worse than a constant. So don't have any negative R squared models. So here is one. I'm going to launch this poll here. Two final candidate models are fit and scored on all of the data. Which one should we choose? One of them has an R squared of 4, one of them is 5. Assume that the model metrics show a slight improvement for model B. Cool. We're getting a good amount of answers in. I think the answers are going to stay kind of in the pattern where they are now. If anyone wants to type into the chat the error with my question, go right ahead. And so right now what we're saying, okay, definitely model B. But I do think that someone, again, I see there's a hand raised. Go ahead and type it into the webinar chat if you have a answer. Okay, neither. That's one. You could explain why neither in the chat. Problem with the distribution is non-normal. Cool. Any other ideas on why this is actually a bad question? Super low. The difference is not statistically significant. Improvement is so small. Good. Is model A the current model? It could be. It's kind of could be either way. There we go. I see it there. This is the one I've been looking for. Stats on the training data don't tell you much. So if you fit a model and you score it on all of your data, this metric I would say is actually completely worthless. It's a small amount anyway. Maybe it's not a good model, but the idea is that if you've trained it on all the data, the most overfit model will always win when you're scoring on all of the data. So when you are when you're looking at any metrics, you always want to look like you're out of sample. It can be training, testing, depending on what you are looking into. Sorry, your verbiage. Some people say test is your holdout. Some people say validate is your holdout. But either way, it should be that or cross-validation. I will say that there is nothing you can tell from training metrics as far as selecting this model specifically with the R squared. Maybe your AIC or BIC could be better here. Let's go for this next one. I think this is an interesting question as well. I'm curious in seeing what people look for here. Okay, so this one didn't make it into my polling, so maybe we can just type it into the chat here. What is a good Gini value for an actuarial model? I know some people were saying that your the R squared was too low here. 4% isn't very much. So I'm asking the group, what do you think it is? What would you answer to this one? Kelly says the Gini is relative for each modeling project. C, but B, if low sample size relative to the other models. Thank you. You're all getting the gist here. And all of you are correct. It depends on the purpose of the model. It depends on your data. It depends on what it is being compared with. And that's the whole idea of this is I do get this question a lot. It's like, what is a good Gini value? What is a good R squared? What should I be aiming for? And the answer is you have no idea without knowing what you're predicting, knowing your data, and giving it a try. It is all relative. Without that relative comparison, again, you can show nothing from this. Now I have one question that I do have. Let's see. Oh, there we go. Okay, let's go there. I'm I'm gonna, you can feel free to change your poll. I put in the wrong question. This has been up for a minute now. But here we have two results. We have random cross-validation, we have year split cross-validation, and we have, maybe this is a trick question, because the last two were trick questions. I don't think this is actually a too much of a trick question. But here is an example where we have random split cross-validation has 10%, year split gives us a 2% R squared, which is not a very good model. Which one should we use here? And I hope this poll is okay. The poll is still open. I see some answers coming through. And so this is something to consider, where usually cross-validation shouldn't change so much based on your split. And some stakeholders might be a little bit wary of having such a poor cross-validation metric. So as people are putting this in, again, about half of you have answered so far. It's evenly split between these and trick questions. So I want to ask you in the chat, what do you think? Like, what is your thought on this? Why did you pick either random or year split cross validation? Confounding seasonality with the year splits. Data prep if R squared is lower between random and out of sample. Potentially environment is changing a lot. If year is bad, we want to know why. There are many hidden correlations in the data. Some accumulation of events in the data. I think that's a very good one as well. For time series application, it's better to go for year split. You don't want to use future data to predict the past. I think that last comment really gets at this particular example. And so this is based on a real life example where this model, this example actually came from a weather peril. And so in this case, I think it was either wind or hail or water. It was something like that. But when you include a geospatial element, you smooth out the residual losses. It turns out that your geospatial picks up a storm, or any of your characteristics can pick up a single storm. And if that single storm is in both your training and your testing data, well, then your model's going to look really, really, really good. You're going to say that like this half of the city is terrible risk. It got hit by this storm. My test data validates that. It got hit by the same storm. My model looks really, really, really good. So what I will say is this is probably what's happening here is some kind of target leakage. And this is something that you would need to use all of your actuarial skills to figure out why this is happening. Again, the answer to a lot of these is, okay, well, why are these different results happening? And the most common reason why is something like target leakage, where there's a storm that's in both. I think that uh, especially where there's large events, this year split is the right way to go. You shouldn't use the same storm to predict the same storm. In this case, yeah, you validate by holding a certain percentage of the data out. But again, if that extra validate data also has the same storm in it, your model is going to continue to look really, really, really good when it's actually not. It's just an overfit model, and you have information in both. The trends include in the depth of the history, exceptional events. To consider in the 2% to 10% is kind of too high. Yeah, I would say that if you are deciding between methods of cross-validation and methods of splitting your data, it should not matter if you're choosing between good methods of data splitting. Because when there's no target leakage, it should fit about the same between these. So the 10 to 2 is just too big to say that's random variation. So if you don't have enough data, you could stratify random sampling with an out-of-time holdout. Yeah, I mean, there's a lot of ways to get around this. I like having the luxury of 5 years of data where you have 4 years in your cross validation, 1 year held out. That's great. Sometimes you don't have that, and you have to make do with what you can and make the best actuarial decision based on how you think you can avoid that target leakage. If you have 3 years of data, it's hard, but you just have to figure out a way where you think you're minimizing that fit. Here, I think this is one that we've already kind of answered here, but I'm going to launch this poll and say, which one of these results is more realistic? You have a team of modelers building fire, theft, and liability models. You're each using the same amount of data, and you're just trying to predict these models, and they come back with these various results. So again, I'll leave this open for just a little bit more time. I think this is one of our last examples before we get to lift charts and maybe some more stakeholder focused presentations or some stakeholder focused problems. Okay, we have 50 people in. I'm going to wait till 60 out of 100, and then we're going to share this. So get those last results, or I'm not. It doesn't seem like we're quite getting there. Cool. We are evenly split on this. So we have a lot of people, another poll has started or shared. Oh, I need to unshare some results here. Interesting. Cool. There we go. It's being shared. So which of these is more realistic? I think this depends a lot on what your data is. I'd say that there's a comment in the chat that very much aligns with my experience, is that liability is very, very hard to model. It's just the severity component can be just wild unless you have very small limits. The frequency is so small, the severity is so high, it's going to be a lot more noisy. And maybe if you have a like top 3 insurer size of data, you can get Team A's results. But for most people in the United States or in the world, Team B is going to be a little bit more realistic with this 4%, where it's going to be this high severity, low frequency, and maybe theft will be this higher frequency, lower severity, much easier to get these results. So I'll say that in general, I think it is Team B, but overall, I'd say it's maybe if you have a lot of data, you can look at Team A. So the real takeaway here is that model metrics, they're really not easily translated into business impacts. I really don't like presenting model metrics to interpret these actuarial, to see if it's a good model. But what I will say is that these model metrics can be too good or too bad. You can signify target leakage if your model looks too good. If you have a peril that could be credible, looks too bad, then I would say, well, maybe the model is poor. Maybe you have poor data quality. A good corollary is loss development factors. You can think about the stability of your loss development factors for this peril. If they're very stable, maybe then your model should also look very stable for this, or your indications. Any actuarial knowledge you have about the stability is very, very helpful when you're evaluating model metrics. But again, a model metric in a vacuum, I don't really tend to care very much about it. It's very hard to interpret a raw number actuarially only in relativities. Lift charts. Now we're getting down to business here. We have interpreting lift charts. These are something that maybe you would present to your stakeholders. Here is a very quick review in our version of lift charts. Purple is the observed, gold is the predicted. Closest to the observed wins. So here I have 2 models. Again, I'm not using a double lift chart. I know I can use those. I would really rather use that. But in this case, model 1, model 2. Is there no clear winner? what do we think is the answer here? So I'm going to launch that poll. Um, hopefully it's out there. Having some issues with the poll here. So if the poll isn't showing up, you can just put it in the chat, which one you would think is better. Model 1 is on the left. Model 2 is the second one. Which one should we go with? Cool. So Model 1, Model 2. We have two. Oops, I meant Model 2 has no lift. Um, good. I think that before I give the answer to this, let's try one more. Let's go to this next one. Here, there's a little bit of a difference where the Model 2 also has oh, sorry. Da-da-da. I don't want to share that. Model 2 now is further away from the observed. So now if you were comparing them, which one would you say is the best? Um, hopefully you didn't get to see my last slide, my next slide there. I see some Model 1s, Model 1, 1. Some people are saying Model 2 in the Q&A. What I will say here is that these results can be misleading, specifically for, yes, legend is too small to read. That's on purpose. Because a lot of people might not focus on this y-axis. And I think that is the key that can be left out a lot. People focus on, is it overlapping? Okay, then I have a good model. But we can see model 2 here, as some have said, it does have more lift. It has more spread. So this one goes a little above that 1.2 segment, and the model on the left-hand side, it has less range. And so I'm going to make a straw man argument here to say that one-way lift charts can be deceiving. Here is a one-way lift chart where my current and proposed, or my current, sorry, my predicted and observed are completely overlapping. This is a good model? No, this is a terrible model. You need to pay attention to that segmentation power. So as people have seen, this y-axis is your lift, and you need to make sure that this lift is actually there, and that is your predictive the spread of your model. And so as some have said, we need to always take into account what the data looks like. So this might not be a bad model if the coverage is extremely volatile or you have very, very small data. So again, as you're interpreting these lift charts, there's really two things to look at. One, the spread, this y-axis, the range that you're getting. Is this what you would expect? Maybe you're building a model, you only get like a 50% lift. Is that enough? Does that make sense? It doesn't matter if you're predicting accurately if your predictions are too flat. And similarly, on the right-hand side, we have little differentiation in this top, maybe 60% of our risks. Is this expected? Or are we really missing something? And we would expect something more like that lift chart on the left where the top decile is really, really poor performing or very, very risky. So with lift charts, definitely spend some time focusing on the spread and the differentiation. So again, I don't really like single lift charts too much, but there is some stuff you can get from that, specifically just raw accuracy. Double lift charts to me are much, much more interesting. So we have this average observed pure premium in each bin, average proposed. So observed again is in purple. In this case, our new model is in blue. Our old model is in teal. Again, the observed the exposures are flat. They're in deciles. As a review, these are ordered by the ratio of proposed to current. So this X where the proposed starts below and then ends above your current is going to happen in every lift chart. The slope might be different, but this X is kind of deterministic. Statistically, the model closest to the observed has the highest accuracy and wins. Actuarially, where are these customers seeing, where they're seeing a large increase or decrease, are these justified? And is our proposed model able to better segment risks? So I'm not going to open this poll because this is kind of a silly one here. But what I will say is that the proposed model is better than the current. It's closer to the observed. It's moving in the right direction. Statistically, it's doing a better job. So now I have questions for you. This is where we really get into the actuarial implications of this. My question for you in the chat is, this is your proposed model is better. If you implement it right now, as is, what happens to the policies in that little circled area, in that top decile? And is this good? So just stream of consciousness, you don't have to type an essay. But if you implement it, what happens? Okay, they're getting a deserved rate increase. That is what I would absolutely say is the highest thing. Yes, they'll pay higher, that they might churn. That is another question where you say, okay, do we care that they churn? Is this something that maybe if these risks churn, maybe that's good. A rate increase may leave, exactly, get a large rate increase, riskiest get the largest, loss ratio improvement. Yes, loss ratio improvement. I do like that last comment. Depending on the elasticity, you will write less there. That is a good point. And so what I'll say is that the distance between the proposed and current is that impact, that change in profitability. But here, that top decile is still operating at a loss. And so what you're going to say to your stakeholders is, hey, we're taking rate here, and it's not enough. So that comment that I liked earlier on elasticity, depending on elasticity, is if their rate is still below the market, they're not going to leave. You're just going to have a less underpriced book, but it'll still be underpriced. So here is something where the question is, I don't think this actually solves a pricing problem. So now that you've decided, okay, we're increasing the rates on these risks, they're still operating at a loss. What do you need to share to help people really actually understand this lift chart? Some of it's already been said. Loss experience is the first question. I'd say that we kind of have that answered here, just saying that loss experience is bad. That's what I would say here. But what else would you want to share with stakeholders now that you've said, okay, this model identifies your top decile and they're getting huge increases? What would you go into that peer review armed with? Companies losing money on this segment? Yeah, I mean, I would absolutely say yes. That's very, very true. Underwriting action, yeah, that's a good one, because what I would say, one thing you can take from this is you're not going to get to profitability with this model. So you need something else to do. And linking to that underwriting action, I'm looking for something pretty specific here. So some of you have already said, yeah, we're okay if customers shop for better rates. They're still underpriced. I think the two things that people have well, one of them has been mentioned before. You want to see what is your bind ratios, retention ratios for this segment. Do we think that we're actually going to see some of these people leave? Are they just going to all stay because we know we're still underpriced? The second thing I would say is you just need to know who these people are. You need to dig into this top decile, cut it apart, figure out where this is happening, why this is happening, what factors are driving this. And that would help you with this, what underwriting actions you need to take. Maybe the step is actually to split this into more and more groups, maybe 20 buckets, and maybe that top group is even more extreme now. And you can get even more targeted with your underwriting actions, because this current and proposed and observed are also the averages. Don't allow new business, great. All of these are wonderful. We're asking all of the right questions. And so We do have other white papers and webinars on how to dig into that. That's not within the segment or in the scope of today. But in general, you want to know who's there at most as possible. Here's a new question. We have a new proposed model. It's the exact same one. We implement the model as is. What happens to policies in that circled area, and is it good? So again, drop your thoughts in the chat. Again, this is a much more accurate model. But what actuarial considerations do we have for this accurate model? And is it good to just adopt the model because it's better? Reduce premium. People will leave if you reduce their premium thinking they overcharge them. Premium drain, leaving money on the table. New model will help retain good customers. All of these are really good. And I think a lot of them are getting at the idea that profitability, at that last comment, yeah, profitability is dropping for these customers. And the way that I've seen these conversations go sometimes is you say, okay, we're taking these customers, we're giving them a 30% decrease. Maybe they're happy about it. Maybe they stay. And then next year you give them a 10% increase due to inflation. Like how do you manage this decrease in a way that makes sense for you and your customers? I mean, I know I don't want to see my bill running around and going up and down and up and down kind of wildly. So yeah, I would say premium drain is a huge risk. One is you're leaving money on the table. You could be increasing your retention ratio quite a bit, or people could see that huge drop, think they've been undercharged and shop. I think those are different perspectives on the market that could be taken care of by your demand modeling. And now, what I'll say is like, what should influence the implementation of this model? What could make this the best model to implement, and what could make this a poor model to implement? So let's see what do we need to know about this section of the model? How competitive, market competitive analysis. That is step one. Are you losing customers in this segment, or are you retaining them? Have you beat the market? Have you identified this great segment, and also of the impact under realistic elasticity assumptions? Yeah, I think that's a huge one as well, is just saying, are these customers going to stay? Are they going to leave? Or how are you compared to um, other competitors? So yeah. Um, and so now let's do one more and say, instead of pricing, this is is there an unfair discrimination test needed? I mean, of course, that I'll say that one is going to be out of scope of this particular uh, section, but the ways that you dig into what's in that segment will help you answer the unfair discrimination test requirements. So the idea of really digging into who is in each of these deciles is that next step, and everyone has their own ways of doing that. But I would definitely have a way to say who is in here, how do I identify them without creating a pivot table every single time. And a pivot table of your modeling data set is going to be kind of ridiculous anyway. But yeah, let's shift for a moment and say, instead of pricing, we're going to use this model for underwriting. Just like a binary yes no inclusion of whether or not we're going to write them. Do any of your previous conclusions change, and how? I see a yes. Cool. That's kind of what I expected. But I guess what is the difference in this model actuarially if it is now an underwriting model instead of a pricing model? What is how does your interpretation change? Yeah. Um, cool. Even more convinced. That's a good one too. I think there's some there's a comment that it won't really affect that bottom area anymore since it's a binary yes no inclusion. We don't really care about the left hand of this anymore. Um, And so on the right-hand side, yeah, it's actually doing a darn good job of identifying those very poor risks. It's an underfit model, to be sure, but it's still doing a pretty good job of identifying these. And this is where a metric like Gini could be very strong for this model. A metric like R squared would be less because it's not getting it exactly. But for this model, maybe it's just the order that you care about. So we're in a really, really good shape for this model. Anti-selection issues. Um, I think that that's more if your model is being poor. If yeah, if you're underfit a bit, there might be some adverse selection that you could uh, better target. But really, where you're not profitable is where you want to target here. So again, lift charts display information on both impact and profitability. So this impact can be supported through this traditional mean, the bind ratios, etc. You can support this chart with information on who's in the highest and lowest deciles. And as always, does this align with expectations? That is, I think, a really, really important one that I've seen in my career is like as we lower or raise these rates, do we expect it? For example, if you have a tier that's been or a tier or a category that has been traditionally very, very bad, or like actuarially you think it's bad. Let's say it's a fireworks depot or something. Like you're writing fireworks depots, and your model says, "Oh, we can lower these rates. That their observe is extremely low. We're doing a very good job at pricing them. We can lower their rates by like 50%." My expectation is that's false. But you might have things like maybe the only fireworks places that you write are really, really, really heavily underwritten. And so that's kind of influencing your assessment of what your model is saying. So because you're heavily underwritten, uh, you're getting only the best risks. And if you lower your rates, maybe you're going to let in some bad business, and you're going to get into that adverse selection circle, uh, your indicated factors. So always, always, always say, does this align with expectations? And where it does or where it doesn't, that is where that weighing of actuarial versus statistical considerations comes from. So we're wrapping up. After this slide, we're going to go into the let's see. Yeah, so we're going to go into the Q&A and just wrap up with our conclusions. But here's a question. You're modeling two perils. There's a pretty stable frequency-driven coverage, 70% of the premium, a more volatile severity-driven coverage, a smaller amount of the premium. You have two modelers. One is strong both actuarially and statistically. The other one is equally strong statistically, but is maybe new to the actuarial world, new to the insurance market. Who do you assign to this first coverage and why? So go ahead and drop some items into the chat if you think you have a good reason for one of those. So modeler one to both. Yeah, okay, cool. But is it modeler two? He can follow the stats. Two because it's easier to model. Um, I think that makes a lot of sense. And the discussion that I would get into here is where are you going to see the most marginal benefit? In your book, is this frequency coverage driven coverage actually very, very stable and you can just follow statistics? And is this application something you can do at the end of the process? Maybe. So if the actual insights can be just like tweaks at the end and not foundational decisions, yeah, I think Modeler 2 definitely can go with coverage one. And so it's kind of getting the idea of what is the marginal benefit of having weak actuarial experience on a stable coverage versus this smaller coverage having that same actual experience applied to it. So yeah, I think that yeah, modeler one to parallel one, because frequency shifts can have much more adverse impact to profitability. That is that's the trade-off, and that's what you would have to get into on your side is it stable enough? Is it relatively stable enough? Because a frequency-driven coverage for one insurer might be very, very different from the level of stability from another insurer. So again, let's just go through these takeaways, and then we'll open it up for Q&A. So again, the volatility of the model correlates with the underlying target. Not all models have equal expectations. Everything is relative. And then following that, output that is too good is likely target leakage. Output that is too poor could be data issues. And this too good and too poor comes from your actuarial insights. Data science can do some amazing, amazing stuff, but still question it if it just looks too good. Lift charts, spread and differentiation. A lot of lift charts look like the one on the left, but if that y-axis is so small, it doesn't matter. Lift charts, instead of presenting these on accuracy, I really would switch to focusing on profitability. So we have an increase in profitability. We want to know who these stakeholders are. And here we still have a profitability gap. So in the proposed, it is below the observed. The company may still lose money on these risks, even though it's better. And so that is the last one here today. We have our decrease in profitability, increase in accuracy. You're going to want all those same support that you had before. And this is the data scientist's conundrum, or the modeler's conundrum, where the better you predict these risks, the more difficult it's going to be to explain to stakeholders, yes, we need to decrease our pricing on these risks that are currently very profitable. This is always a tougher decision than the other side of the lift curve. And it all comes down to weighing the statistical and actuarial support. So implementation decision, you have the bind rates. During the modeling process, you have statistics. Is it significant? Are these p-values good? Is it regularized out of the model? Is it getting the best cross-validation test statistics? Actuarial, is it implementable? Is it consistent? And so, yeah, there's a lot of things to consider. I see a comment of, if you don't look at opportunities to outcompete other market players, yes, all of that I'm really just bucketing it in the actuarial considerations and those post-modeling analyses and those post-modeling selections. So this interpretation of lift charts is very, very light, very, very like, this is profitability. I would include all of those demand assumptions, and that all depends on the data that your company has at hand and how much time you have to go down that modeling rabbit hole. So I'm going to open it up for questions. I know we had several hands raised during the presentation that I ignored and only went 4 minutes long. But I'm going to leave up this for some upcoming webinars. There's two coming up, one on the introduction to machine learning by my colleagues Par and Max, and then a webinar on penalized regression and lasso credibility using a case study to show how lasso can be a strict credibility procedure. And so any thoughts if you see a lift chart that has higher lift in the observed line than the predicted line? So I'm going to answer this one. And I think that higher lift, if I'm correct, would be essentially the same as here, where the observed is going higher than the proposed or the predicted. And this is when I would generally say that is an underfit model. You're not reacting enough. So what you're saying is you segmented risks by you're ordering them pretty darn well, but you're not fully reacting to how you've ordered them. So this is something where I'd say, yeah, I think your model is just underfit. You have room to surcharge. And this is the result that I would expect when you are implementing a model with maybe capped factors, where you're going halfway to indicated or like most of the way to indicated. You're never going to completely get to that observed line with your proposed rates, but you can start getting there. So that would be my answer if you see a lift chart that where it's not quite to that observed area. Any other questions to type into the Q&A or the chat, or any examples we want to revisit? I know I kept it very high level during some of the discussion to get through the topics, but I'm willing to dive in for another 15 minutes if there are items to discuss. Okay, I'm seeing some people drop off. Q&A. Can you discuss removing the log term again? Yeah, we can go back to this one. This example, I will say, was kind of a false choice. It's one where I asked everybody to choose, even though it was obviously you do something different in practice. And so here, uh, with the point that I wanted to make here is that polynomial terms fit very, very well where there is data, but then they can extrapolate pretty highly. And so one thing that uh, can happen is that where you have data, it can fit very well, and then it extrapolates elsewhere. And so this extrapolation is not what's actually improving the model. What's improving the model is over on this left-hand side, and the right-hand side is something that is not going to be fileable in any states, and it's not even supportable by the data. It's because of this variable transformation. Um, that's what's happening. Is anyone really using high degree polynomials in their models? I'd say like in my past lives, I think I've used some higher ones, but maybe not for terms. But I think the idea of extrapolation is something that I would relate anyway. It can happen with squared terms as well. And the choice between fitting a single linear or squared or log term, even that single one can really extrapolate in directions that maybe you don't want it to. Is there a moral obligation from the precepts to not continue overcharging the best risks? Um, so I think this is where there's a lot of discussions on how do you have like a fair treatment of your customers. I think getting all the way to indicated is something that is a goal. But also if you there's kind of an understanding in the industry that if you go all the way down on one segment, you're going to go all the way up on another, and that is something that is less acceptable regulatory sometimes if you have these huge increases. So I'd say I don't think the precepts talk about moral observations. But I'd say that the idea of eventually getting to that charged rate is the goal, and how you get there. So getting to the most accurate rate is the goal, and how you get there is open for like regulatory restrictions and other discussions on how you get there. Sounds good. If you're hearing anything in the background, I'm in Chicago and the Air and Water Show is testing up and a jet plane just flew over my house. So I'm going to wrap things up. Thank you for the questions. Feel free to follow up via email or any other way that you want. And have a great rest of your day. Thank you, everyone.